So last lecture we were looking at this situation here to use it for defining different forms of pressure that we use in engineering. The static pressure, stagnation, dynamic, and total pressures. These are words that mean something in terms of our measurement of pressure. All of these. And to pick up a little bit, so recall that we have for the Bernoulli equation along a streamline, P plus 1/2 rho v squared plus gamma z equals to a constant along a streamline. A streamline being a curve which is tangent to the velocity vector everywhere. Okay, so we apply this in this situation over here at different points. We looked at the pressure at point point 1, and using our manometer analysis that we've done before, we obtained that P1 was simply equal to gamma H. And that's no surprise there. P1 is equal to gamma H. So the pressure at 1 is simply the hydrostatic pressure there. Okay? So basically, from this equation, from this equation, then gamma z is basically hydrostatic pressure, right? This is no surprise here. And this would be the pressure as measured by a piezometer. As we discussed in the section on manometers. Okay, so now we want to look at the pressure at the point 2. So in point 2, a element of fluid that is following along this streamline here, passing through here and comes to here, at point 2 comes to a complete stop. So the velocity at point 2 is equal to 0. It comes to a complete stop because this is a little tube that is closed here to the back. And so there's nowhere for that particle here of fluid to go. It just stops here. Velocity at 2 equals 0. And so I use my Bernoulli equation to find that the Bernoulli between points 1 and 2 basically I'm getting ahead of myself. 1 and 2, and I see that P2 plus 1/2 rho V2 squared, which is 0, and we consider Z1 equal to Z2 here, so we don't have to worry about that third term, so that is equal to P1 plus 1/2 rho V1 squared. I want to make sure some people are looking a little bit either sleepy or confused. So tell me if there's anything not clear so we can explain it. I wish I could read your faces and know exactly, but I don't. So if you tell me, I can try to explain it better. Okay, good. Thank you. Thank you for your question. Okay? There is a little line here where the flow must be continuous because it's a streamline. Okay? So as velocity approaches as a fluid approaches any obstacle, suppose that we have a airfoil in the flow. As the fluid approaches that obstacle, right, if it goes around here, it will go around. Oh, sorry if my... Okay, it'll go around somehow, like that. If it approaches here, it'll go around perhaps somehow that way. But there's one streamline which will hit right there and will not go anywhere. one streamline where a particle of fluid simply decelerates straight to zero. That is called the stagnation streamline, and there's always a streamline there. Basically, in this picture here where we have an airfoil, there's half of the flow goes at the top, half of the flow goes around at the bottom, but there's one streamline that divides what goes from the around the top and what goes around the bottom. That streamline is called the stagnation streamline. Okay? This guy here, stagnation streamline. And that point, there's always one point, well in this case actually there's 2 points around this object, which are stagnation points. These are the points, 2 points around this obstacle where the velocity has gone to zero, okay? And basically everything above it, all the flow, has to go around the obstacle. What we have here is the same situation, an obstacle. The obstacle is this little tube. The back of this tube is that it's a flat wall. The fluid runs straight to that wall and must stop. Because everything inside this tube, all the liquid inside this tube is static. It's not moving, it's not flowing out here. It becomes static. However, the height of that column is higher than if it was just the static pressure because of the effect of that pushing of the fluid that has come to a complete stop here. Yes, another question.
How many stagnation points are there on a flat surface?
If it's just a flat surface and I have a jet coming to it, then I have a flat surface here. I mean, suppose that I have a fluid jet. Let me change the color for the water so you see it more clearly. And I have a fluid jet impinging that, like the case of the veins. But the fluid just turns around, half goes to the top and half goes to the bottom. Like so. There's only one point here, that is the stagnation streamline, one stagnation point. Now, the velocity all along this wall is zero, okay? But in this area over here, we have a distribution of velocity that goes from v to zero. Say if I were to make a zoom to that area, it would look like so. I would have the velocity, I have the edge of the water jet, and perhaps the velocity would be going from a maximum to zero at the wall. But the streamlines there are all, aligned nicely with the jet. Whereas at this point, the streamline right next to that point is going up, the streamline right next to the point at the bottom is going down. The fluid must be continuous, so between a positive and a negative, if you will, there must be a value zero. Because the fluid is a continuum, we're in the continuum approximation. We are not looking at what every single molecule is doing. Perhaps the molecules, if I really, really go deep into the atomic level, there's all sorts of things going on there, but we're taking the continuum point of view. Infinitesimal. This is the continuum approximation. It's a mathematical abstraction of what really is happening in the fluid, which gives us a tool to study fluid mechanics, right? So we are able to, when we write all of these differential equations, we are making an abstraction, a mathematical abstraction of what really is happening there physically, which is consistent and gives us, consistent with the physics, okay? But does not describe what every single molecule of water might be doing. At the atomic level, other things go on, okay? But this is, at a macroscopic level, this is a good approximation where we have the power of mathematics to explain what's going on. Okay? Yes?
So this doesn't explain why it's very good at water since what it comes back to you. It just describes the
For yeah, this is a quite an idealization. I mean, you would have to have perhaps some shape here that is irregular, so that some of the streamlines approaching that have the chance to do that. Or, the water, there's surface tension effects and all sorts of things that we're not considering in terms of what you see in real life when you just grab a garden hose and spray it on somebody, okay? We're looking at very simplified abstractions where we can use mathematics, but where it turns out the equations and the physical principles that we use, such as conservation of mass, conservation of momentum, and today we will discuss conservation of energy, are in fact entirely justifiable and very useful because they give us answers that we can apply for engineering purposes, to design engineering devices, where perhaps if we're designing a turbine that has some vanes like that, and we should shoot some water here to make this turn, right, and generate electricity, we can perfectly well use conservation of momentum to calculate torque here. We can perfectly well use conservation of energy and not worry that one little particle of fluid actually turned into a drop and jumped out of this whole system. It's on average a very good approximation. So these are sort of idealizations a little bit, but which are perfectly justifiable. And from that point of view, in the limit, basically, because we're using a continuum approximation, then all of our calculus applies. And as you know, a function in calculus, if it goes from positive to negative, has to go through zero at one point. In this situation, again, as the velocity goes from positive to negative, in this picture right here, right, positive y direction, negative y direction, at one point it must be zero. Just out of the wall here, basically, the streamline comes to a complete stop. The fluid stagnates. That's why we call it stagnation streamline. That's the concept that we use, and it turns out to be very useful. Is that better? Yes? Good. Thanks for your question once again. Okay. So we are looking at this situation here where we have applied Bernoulli's equation exactly on the stagnation streamline, which is drawn in red on our sketch of the situation. So velocity at 2 is 0 for the reasons we've just described. Velocity at 1 is the velocity we're considering now, again, sort of simplifying the situation, a uniform velocity inside this whole pipe, and it's v1, our average velocity. So on the point 1, we have p1 and 1/2 rho v1. So what this is telling us here is that the pressure at the stagnation point is larger than at 1. We're adding a positive number, 1/2 rho v squared. And this is what we call this quantity, the quantity P plus 1/2 rho v squared, is what we call the stagnation pressure. The stagnation pressure is the largest pressure that can be obtained in the fluid if we neglect the effect of elevation. Remember, we've neglected elevation changes altogether. So in that situation, stagnation pressure is the largest pressure that we can obtain when all of the kinetic energy basically has turned into pressure, a pressure rise, shown here in this sketch as a rise in the height of fluid as would be measured by a manometer. Yes?
Is it like a sudden stop or a gradual stop?
Gradual stop from V1 all the way to 0.
So if you chose V1 and something farther, stagnation pressure.
Well, V1, this is sort of unperturbed in the pipe, and V, or V1, is the same everywhere, right? And if I'm standing a little bit around here, what's happening is the fluid, is going around this obstacle, right? And so V, just around this kind of perturbed area will be adjusting to the obstacle. But we're looking at the places where we know things. We know at one at least, we know the velocity is the unperturbed velocity and the pressure is the static pressure there. And from 1 to 2, we can apply Bernoulli's equation, where the only unknown at 2 is the pressure. And it turns out that it's basically like we can interpret this as the sum of both the kinetic energy and the pressure have all been turned to pressure at 2. And so we have the static pressure, which is this one over here. So we have static, we have stagnation, which is that one. Now we need dynamic pressure. Dynamic pressure, we just call this term over here. We agreed to call just 1/2 rho v squared, that term. We agreed to call this one dynamic pressure. We got that one. And the last one is total pressure, which is the sum of all of them. So total pressure is P plus 1/2 rho v squared plus gamma z. That's the total pressure, the sum of static, dynamic, and hydrostatic. Hydrostatic being gamma z. Static, dynamic, and hydrostatic. The sum of the three is total pressure. This is our engineering consensus in terms of the terminology that we will use. Yes?
Is it right to say that at one total pressure is equal to gamma H? Or is total pressure something that we use the entire?
Total pressure is P plus 1/2 rho v squared plus gamma z. And gamma H just measures P, the static pressure.
So then total pressure applies to the whole system.
The total pressure applies at this point, at any given point, by the sum of static is gamma H, dynamic, 1/2 rho v squared, and gamma z if there was elevation here that we would consider in addition. Now, in this point, the dynamic pressure has gone to 0, and the static pressure has increased, but the total pressure did not change. And that's what Bernoulli's equation is telling us. Bernoulli's equation, we can interpret Bernoulli's equation as saying that the total pressure is constant along a streamline. So it can only be changed from one form to another, but the total pressure must be constant. You see? P is gamma H, and this gamma Z that we're talking about is actually comes about from the elevation effects in a whole system. So if we had, it disappeared. Okay, good. So I have that spaced. If we had the same situation here with our piezometer and our dynamic pressure measurement, but this whole thing changed elevations, then we would have a different in gamma z. But here we've taken z1 equals z2, so we've simplified our analysis at just this little place over here. We don't have the effect of z. But still, gamma h is the static pressure at this point, if I look at that piezometer there. Gamma z is for elevation, yes. Yes.
So it was flat, when was the before that?
Exactly.
And so
Gamma z term only represents changes in elevation, and that's going to be useful when we look at, for example, a system where we have a hydroelectric pump, a hydroelectric turbine. How does that work? We have a change in elevation from the top of the mountain to the bottom, and that, as we go down, the mountain becomes dynamic pressure. We reduce gamma z, increase dynamic pressure, and then we turn that into here on a turbine. We turn the energy, we grab that energy to generate electric power. That's how it works. So, important last conclusion of this is that the Bernoulli equation says that total pressure is constant along the streamline. Good? So we can apply that concept now for the measurement of velocity. And we use that in a device called the pitot tube, very classic device, sometimes called the stagnation tube, again because we would have a streamline here that goes from a velocity greater than 0 all the way to 0 over here. So it's an open-ended tube which when we put against some sort of wind, some incoming fluid, if we connect this to a pressure sensor, a manometer for example, or any other sort of pressure sensor, will give me the stagnation pressure because the velocity is 0 here. It goes to 0. Well, we can say 0 here because all of this air or all this fluid inside the tube we can consider to be 0. And so this is here a stagnation point. And therefore the velocity equals 0 there. And so we get stagnation pressure, basically the same situation we had before. So if I want to draw the situation I had before inside a pipe, oh, forgive my crooked lines there, and this would be all the fluid here. Then we would have points from points 1 inside the pipe to point 2 right there. Then we'd have some fluid height there. Say let's call this one H, and to this level let's call this one D. That say it could be the diameter. No, this radius. Let's just call it D. And this Z1, of course, is equal to Z2 approximately, with good approximation. So at point 2, we have the same situation we had before. P2 plus 0, because V2 is 0, equals to P1 plus 1/2 rho V1 squared. And so we can use this to determine the velocity inside the pipe. Because if I don't know the velocity inside the pipe, but I do know the pressure, then I can solve for V. So V1 squared is equal to 2 over rho times P2 minus P1. And say P2 is, if I measure that height, it's going to be gamma times H plus D. P1 is going to be gamma D simply. So I put that in here in the equation. I have gamma H. Basically, this is gamma H now. The little h. Which means I can solve for V. V1 is equal to square root of 2. Gamma is rho times G, so I can cancel out the rhos and simply get GH. And this is the Peter tube equation. Or stagnation tube equation. So now we can have another device, which is, let me see if I have it right here. Okay, so basically another device which is similar to this. So look at that Peter tube now, and we're going to add another little opening there, which is perpendicular to the flow, like shown here. So the opening in the middle, again, as before, is measure stagnation pressure. But if you imagine that this tube is actually like, well, tube shaped, and we've put some little holes on the side which are perpendicular to the flow, then these are going to actually measure the static pressure. So this is a static pressure tap over here. The flow is going like before, right into the stagnation opening. So that tube is aligned with the flow in that way. So this little tap here is perpendicular to the flow. This one is right front, and so we again have a stagnation point there. Okay, now we're going to do something a little bit tricky. So we're going to look at this point, and we're going to do a look at, well, let me draw it here, this point. So it's right next, it's an infinitesimal point right next to the opening there, and this one, and I'm going to look at basically the streamline that goes around here. Okay, and this is going to be point 1, and this is going to be point 2. So it's a streamline that is passing through points 1 and 2. Because the flow is continuous, I'm basically looking at one streamline that is just right next to the pitot tube, and I'm going to be content with the approximation there that I'm making that is right next to the stagnation point so I can apply Bernoulli. So Bernoulli on that streamline and I will have, well, P1 plus, let's put the whole thing, rho V1 squared over 2. That one will cancel out, but let's just leave it for the time being. So we're going to take Z1 equal to Z2 and cancel that one out. And P1 we're going to take to be the stagnation one, so this is equal to 0. As before, we have that V2 is equal to square root of 2, the same thing we just did, P1 minus P2. And we use this to measure velocity. Yes.
So the pressure at 2, that's the static pressure.
Correcto mundo, yes.
Isn't the airflow at 2, is the airflow at 2 moving?
Yes.
But it's the static pressure. I don't know, that's just confusing to me.
The language is confusing to you? Yeah, we call it the static pressure, but basically the name only applies to the actual thermodynamic pressure, the P that appears on all our equations. We just call it static pressure, to differentiate it from dynamic. Dynamic pressure is the one that only comes from velocity, the velocity term. So it's just the language that was chosen historically. I can't really explain it.
But the airflow isn't, it's not like stopped, like it's not, the V is not 0.
Where? At 2? No.
Like it is at 1.
No.
So it's not static.
So we were basically, remember when we were talking about the airfoil, we said this is going to come to a complete stop, so it's 0 here. There is a streamline where the velocity is, accelerating or decelerating. Yes.
I think what he's talking about is that the streamline doesn't actually enter the static pressure line.
Yes, I said I was going to do a little trick here because we're kind of looking at just next to the tube and following it around, and we're kind of cheating a little bit, yes. But it is a good approximation so that we can use the measurement of these two pressures to estimate the velocity, within engineering, acceptable accuracy.
Taking it down to a very small static pressure chamber line that runs through that piece of you can kind of say that because it's pointed orthogonal to the flow, the streamline can't enter.
The streamline does not enter here, right? This is it's the same as when we had the piezometer, and there was a tube here, and the fluid is inside. The fluid is flowing this way. Here we just have static pressure.
So a little static. Do you have fluid in there? And that's how you know.
Yes, we have fluid, but the fluid is static. It's not moving. And this fluid, when we're measuring, for example, the pressure used for a piezometer, the fluid in here is not moving. But here it is. It's passing through there. So basically we use this to measure velocities. This is using a differential manometer. So with a differential manometer, we can measure delta P, and we write V2 equals to square root of 2 delta P over rho, and we obtain velocity from differences in pressure. You will do this in your lab, which you should be starting this week. You will use differential pressure to measure velocity, I believe. This is also used, of course, for measuring the velocity in airplanes. So what you have in airplanes is same device that we have shown before. It's well, we call it a pitot tube, but it's really a pitot static tube, but it's just too long. People don't want to say that, so they just call it a pitot tube. Pitot static, why? Because you can't really see it here, but right there, there's a little tap, there's a little hole, right? That actually is measuring the static pressure, in addition to the little hole at the front that is measuring the dynamic pressure. The difference in between the two pressures provides the quantities that we use to measure velocity. So this is used to measure the airspeed of the plane. And we need to use both a static and a dynamic pressure tap in this case, because we can't just use atmospheric pressure and take a value, the standard atmospheric pressure, because the plane is, of course, changing elevations, and the reference pressure is changing as the plane is flying at a higher altitude. So we have to measure the static pressure of the air and also the dynamic pressure of the air and obtain the velocity by the difference of the two. And here are some other ones. Sometimes some planes will have two for reliability in case a bug flies into one of them. And you will have usually these protectors with this long red thing that says remove before flight. Again, that's just protect from the bugs, and they are removed before flight, hopefully. There's been cases of them not being removed, and this resulting in some mishap of the pilots not being able to read speed, of course, airspeed. And here's a person removing the little protector from a pitot tube that you can't really see because of the size of that plane. Okay, so now you know what that pokey thing in the beginning was, in the beginning slide was. Yes?
You're saying that the whole front measures the
Stagnation pressure, I'm sorry. I must have used the wrong words there. Stagnation, so dynamic plus static. Forgive me, yes. I guess it's a good time to have a little break here, because you must be tired.